This PowerPoint presentation covers how to calculate an equilibrium constant for a reaction of a weak acid with a weak base. So far, we have learned how to find the equilibrium constant for a weak acid or a weak base reacting with water. As a review, recall that Ka is defined as the equilibrium constant for the reaction of a weak acid with water. Kb is defined as the equilibrium constant for the reaction of a weak base with water. We've also seen that we can find the value of Kb if we know the value of the Ka of the conjugate acid of the base by using the expression Kb is equal to Kw over Ka. And recall that Kw is the ion product constant of water, which has a value of 1.00 times 10 to the minus 14 at room temperature. But how do we calculate the equilibrium constant for the reaction of a weak acid, not with water, but with a different weak base? Say, for example, for the reaction of Ha with the base B to form Hb plus and A minus. The equilibrium constant is of course defined as the concentrations of the products over the concentrations of the reactants. But how can we find a value for this K? It turns out that we can do this by combining reactions of weak acids that we already know. First, let's look at how to predict whether these reactions will be product favored or reactant favored. The reaction will favor the stronger acid reacting with the stronger base. If the stronger acid and base are on the left side of the equation, the reaction will be product favored. To determine this, we first need to know which acid in the equation is stronger. In this reaction, which species are the acids? Well, we have Ha is the acid on the left, and the Hb plus is the acid on the right. To see which acid is stronger, you can compare the Ka values for Ha and Hb plus. In the example shown, the Ka value of Ha is larger than the Ka value of Hb plus, indicating that Ha is a stronger acid than Hb plus. On the other hand, if the stronger acid is on the right side of the equation, then the overall reaction will be reactant favored. Let's see how we can quantify these predictions by actually calculating a K value for a specific example. The example shown is the reaction of the weak acid ammonium with the weak base hydrogen phosphate to form ammonia and dihydrogen phosphate. The acid on the left is the ammonium ion, and the acid on the right is dihydrogen phosphate. Which acid is stronger? If we pull up the Ka values for these two acids from our reference table, we see that the dihydrogen phosphate is the stronger acid because it has a larger Ka value. Therefore, this reaction should be reactant favored with an equilibrium constant value that will be less than 1. But what is the value of K for this reaction? If we break apart the overall reaction into two pieces, we can calculate the overall K. Notice that the ammonium ion is being converted to ammonia in this reaction by losing a proton. If we show just this part of the reaction, the conversion of ammonium to ammonia with the production of a proton, we recognize this reaction as the Ka reaction for ammonia. What's happening to the hydrogen phosphate? The hydrogen phosphate is picking up a proton to become dihydrogen phosphate. Let's write this reaction out. This reaction isn't a Ka reaction, but if we look at it backwards, it actually is. The reaction of dihydrogen phosphate, the product, to form H+ and hydrogen phosphate is the Ka reaction for dihydrogen phosphate. Remember, we learned in chapter 13 that when you turn a reaction around, its K value will be the inverse, or 1 over the original K value. So the K value for the second reaction shown here is 1 over the Ka value of dihydrogen phosphate. If we add these two reactions together, we get the overall reaction that we wanted. Recall also from chapter 13 that when you add two reactions together, you can get the new K value by multiplying the individual Ks. So the K value that we're looking for is 5.6 times 10 to the minus 10 multiplied by 1.6 times 10 to the 7th, which is 9 times 10 to the minus 3. Notice that this value is less than 1, which is what we qualitatively predicted before. In this presentation, we saw how to determine the equilibrium constant for a reaction of a weak acid with a weak base by breaking the reaction into two reactions for which we know the Ka values. This is an important concept or skill that will be used again in your future organic chemistry courses.